Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is my pleasure to have Professor Zhuowen Tu here to give a presentation on his most recent research work on vision and biomedical image analysis. Professor Zhuowen Tu is from UCLA in the Department of Neurology as well as Department of Computer Science. Professor Zhuowen Tu has done a lot of great research work in computer vision. He got the MR Prize in ICCV 2003, and recently also got was that first prize on Grand Challenge on brain image segmentation. And yeah, I will leave Professor Zhuowen to give his great talk here.
Okay, thank you so much, Ken. So yeah. Today, I'm going to mostly focus on a recent work I did last year and this year about object recognition in general. And the focus is about the context, but it's more about modeling and computing. So context comes from a lot of so-called within object parts and between objects, different configuration. And recently, context has become a very important concept in the computer vision or even machine learning field in general. So anybody guess what this is?
It's either Australian art or it's a tiny microscopic organism.
Yeah, that's a very good guess. So sometimes it's very hard to see. But if I present you with another thing, you can immediately tell this is a snake. Even the middle part is occluded. So that's why context is really important. And then appearance definitely helps you to tell it's Australian artistic drawing. But what it is, any guess?
Water. Is it like the intestine?
Yes, yeah. Yeah, that's right. So again, this says how important context helps us to understand the object in general. So some related work, recently people are trying to so-called conditional contextual models for object recognition, also boosted so-called boosted random fields and also spatial boosted, things like that. People are trying to learn pretty much a appearance model, then try to combine the context in a conditional Markov random fields type of framework. So I'll just go to the problem directly. So now suppose we have data observation X as a huge vector. You can stack all the pixels together as a vector. So now suppose you have a ground truth Y, which is the label for each pixel. So if it's an object segregation problem, it's 0 for the background, 1 for the label of interest. If you want to annotate all the different objects, so for instance, roof or building, trees, things like in general, then for each pixel, it has multiple choices, possibility for different labels from 1 to k. So in this field, Bayesian approach has been popular. What we want to do is, given a data X, we want to estimate, compute, learn, model the posterior distribution, and pretty much we can separate the posterior into likelihood and the prior. That's a typical thing we do. But it's really extremely difficult task because first, even now, there's no any satisfactory likelihood model out there. You can say, I give you this kind of roof, can you give me a precise model? It's hard because everything is joint and it's a texture, all these things. And it's not a homogeneous texture, and also it has the lighting, all these things. And also prior there's a prior about different objects, there's a prior about the shape for each individual objects. And if we put them together, it's a huge complicated thing for us to put all this configuration all together and make them into elegant statistics. So I pretty much summarize the challenges is two parts. One is modeling. How do you really learn a faithful model for the general scene image understanding problem? Then another thing is the computing. So even you have a model. So now suppose you can overcome or simplify your model a little bit. Suppose you have approximated the posterior model. And how do you compute for the optimal solution is still a very difficult task. So that's the major challenges in computer vision, machine learning in general. And so here, we want to put the context into this picture, but to make the whole computing or learning framework very simple and straightforward, because there being lots of work in terms of modeling, in terms of computing, belief propagation, graph cards, recent many of the recent thing modeling, MRF model, CRF model, all these things. But there's big major problems with the existing Markov Random Fields model, belief propagation, or CRF, Conditional Markov Random Fields model. So all these models pretty much use fixed topology, unlimited number of neighborhoods. There's always pretty much clique with pairwise relationships. The energy function is very restricted. Usually slow. It takes many steps for the message to propagate from just like seeing a snake head. We can immediately propagate this message to the tail. But for the existing models, it's almost hopeless. There's no guarantee, not guaranteed to find the global optimal solution. And again, the modeling and computing process are separate. Even you have a good model, you have to engage additional set of computing mechanism to perform energy minimization or optimization, which is often very slow for complicated problems. So now, actually, I can go directly to this algorithm. So suppose these are some segmentations we obtain, and these are the solutions Y, and these are the images. So as we can see, there's huge variation in the foreground and there's huge variation in the background. But given all the knowledge we have, we can more or less precisely segment the object of interest. So now, what we want to do, instead of studying the whole joint status given image, we want to study the whole joint status of every pixel in terms of Y. Let's study the marginals. So given image, we want to decide how likely there's any particular pixel of interest belonging to the foreground or background. So turn this thing into a marginal probability. But ideally, if you want to really obtain this marginal probability, oftentimes we need to integrate out all the rest of the pixels. For instance, if we would say how likely this pixel belongs to the horse body, you need to integrate out all the neighboring pixels because they are in the joint probability space. So studying this marginal seems to be even a more difficult problem because of the integration. But we can turn the course around to make the problem simpler. So suppose we face, let's consider a traditional classification problem. I'm giving you an image, and the task is to perform segmentation, foreground and background. And let's say, suppose we have a training set. This S has all the image patches, and for each image patch, there's a label. So now each I is a pixel here, and we just crop up image patch. And each image patch has a label associated with it. It's very simple. So if we do this, we can collect two bags. One is a positive bag, another one is a negative bag. So positive bag contains all the patches for the pixel in the center on the object. So these are the positive. And you can collect all the negatives or the background into another bag. We can perform any kind of classification in this kind of screen. But it's very hard because when we understand or segment an object, we have all these middle level, low level, high level information in there, which allows us to segment the object or understand, recognize the object. But if you would only look at the image patch, there is certain information. For instance, this head of horse is very dominant. But many of the structures are very hard to tell. So that's why you can put it in a logistic regression formulation, but you won't get very good results because it's intrinsically difficult to separate them. So then auto-context it's an extremely simple algorithm. Suppose now we have a training image, we have the input image, you have the ground truth label. You can perform first level of classification on the image patch. Your favorite classifier, your favorite features. You obtain classification map like this. So as I said, for certain structure, probably it's dominant, but many times it's fuzzy. So what we can do here actually is now at each pixel, we have image patch you can compute features. That's appearance. So the question is, how do you combine this kind of so-called prior or the configuration of different objects or even the single object for different parts? So for any pixel here, you can shoot out the many rays. And in your classification scheme, you also collect the the probabilities on these rays. Or you can even put the gradients on the probability map or classification map itself. And you train a second layer of classifier. So in the first layer of classifier is trained on the appearance only. Then the second layer, so once you have a probability map output from the first layer, so now you augment your classification feature pool. Not only you have the appearance features now, you also have the probability map or the context from the last time, so from your classification map. So definitely the probability is going to be enhanced so for the blue dots are all the candidate features. These red ones are the features picked by the classifier. So it's like we're trying to build a dynamic graphical model. In the traditional graphical model, the connections is very limited. But here, we allow the algorithm first to automatically learn what are the supporting features or the sites. These sites can be either near the current interest pool or it can be far away. So the message, if something indeed is really dominant or informative, the message can be immediately propagated from the other sites. And also, we don't throw away the appearance feature. Appearance features are also over there. Just up to the learner to decide whether the appearance is more informative or the context informative. Yes?
So do you use the classified result from the classifier 1?
Yes.
You build a classifier 2?
Yes. Yeah. So this is the classification map out of the first layer of classifier, purely on the appearance. Yeah.
So many times when I think of context, I think of context as using information about the object surrounding the object you're trying to recognize.
Yes.
So here, you'd recognize that this is grass, which makes the horse more likely,
Yes.
that sort of thing. So, but there's a lot of different definitions of context.
Yes.
So is your definition of context then context within an object? So I want to use the context of the horse's legs and the head to then help.
Yeah, that's a very good question.
Say what the horse is. Is that more in line with what you're defining context as?
No. So that's a very good question. So context, as I said earlier, just like you described, context most time are from between or different objects as a context. But one major thing for context also is for a single object, the context can also come in different parts. And so the mechanism I'm going to talk about later is this mechanism does not distinguish between either within or between. It's all up to the learner to decide. What if we have multiple labels? I'll show that what you have is just multiple classification map on different labels. And also the algorithm, the classifiers are fed with all these different contexts from different labels. And then it's up to the learner or classifier to select them. So everything is automatic. So if the
classifier might actually pick up on the grass.
Yes, yeah. I'm going to show you later. Yeah.
Fixed scale. I'm not understanding the role of scale in what you just
That's a very good question. So once we go through, I'll talk about that. But here, at this moment, you can consider it's fixed in terms of skill, but later on, you can add skill information. But once we go to the more or less the later part of the talk, you will see. Yeah, that's a very good question. Yeah.
My understanding is that the learner will automatically pick either this kind of in-object context or outside object context. But if you have any sort of for this host object, what's the portion of the features and segment or classifiers you then?
Yeah. So here, it's very hard to say because for any pixel, it shoots out these rays, right? So there's no kind of within or different because here, there's only one classification map. But if you have multiple classification map, you will say if the sky is dominant, then these things will help to support. That's for sure. But so for multiple class, so the local like the within class thing helps you support with local ambiguity. But for a multi-class object, sometimes if one particular, I'll show you later, one particular type of object is really dominating and supporting this decision, then these things are often being picked up by the classifier. So then you can see the class. So then next level of classifier will output another classification map. You can see the map has been greatly enhanced. And you just train another layer of classifier. Now the algorithm actually chose different set of supporting classifiers based on the current one. And this is pretty much after 4 iterations. You can see the classification map has been greatly enhanced because of all these supporting things selected by the.
When you say iteration, is that I mean, it looks like a layered system.
Yes.
It's really layers.
Yes. So you just train. It's not a cascade. It's a series of a sequence of classifier. So the iteration meaning just a couple of classifier. So in one sense, you can consider it's performing message propagation. But here, the message propagation acts in a much more efficient way than the traditional belief propagation because it's first you don't need to compute the integration explicitly. You just compute the logistic regression, so it's closed form. And then, and second is, all these supporting things are much more informative, and you can afford to have 1,000, all these supporting contexts, but still can be computed within like milliseconds. So what the algorithm is doing actually is trying to learn or compute the marginal distribution conditioned on the previous classification or probability map. So what we want to do is, by doing this, we're hoping that we can approximate the whole true marginal distribution, but without doing this explicit integration. So the features, then you can compute the appearance features on all these gradients, even like the face detection, like a Viola juice type of features can be used. And also context, you can let the algorithm to select fairly large number of context information in this framework, and it's extremely simple. But actually, I said the first classifier is different from the second one. At this point, I can take back the argument. The first classifier actually is identical to the second one. The only difference is in the first classifier, the classification map is a uniform distribution. So now you don't have to distinguish the first one or the later ones because everybody shares the identical procedure and code. The only difference is you start from an initial map. But this is for this particular application. In some other domains, you can know roughly where the foreground appears. Then you can input the system, give the initial system with an initial classification map. Then the algorithm starts to justify, refine all these things. So it's again, it's extremely simple algorithm. You can see the classification map are being enhanced. If there's a wrong thing, the probabilities are being suppressed. Then if there are all these weak things, you can see the probability maps are being enhanced.
I'm trying to get a picture here. The classifier is only binary, yes or no. It's not part of the horse, or is it sort of knowing every part knows its where it is on the horse, so it expects another part to be at another spatial position, or what is happening here exactly?
Yeah, that's a good question. So there's this explicit and implicit part type of thing. Here, there's no explicit notion of where the parts. It's kind of good or bad. Good thing is in the annotation stage, there's no confusion. You just say yes or no. It's up to the learner to select. But the bad thing is that this kind of information is implicitly buried. Yes.
So conceptually, if I shuffle the pieces here, the support that a part gives to its neighbors is just that it's present. It's not how it is related to it. I could turn the horse upside down and it would still do the same thing.
Yes. Yes. Yeah. But so the classifier is trying to decide. The decision is 0, 1, but the features are probabilities. So it's a confidence. It's not a hard decision.
One place would be affected by its neighbor in the sense that there are other horse parts around. It doesn't care where they are. They're close.
Close. Yes. That's right.
Do you have a different classifier for every pixel in the image?
No.
So it's the same classifier?
Yes.
Okay, and it doesn't depend upon the spatial relation. Like the classifier, you have some things marked in red and blue. Can you describe what the red and blue mean?
The red ones are picked. So blue ones are blue, and the red are the candidate features or candidate context. The algorithm does not pick them all. The classifier does not pick them all.
If you're red, it doesn't care which red one you are. It puts all the red ones in one big bucket.
In one big bucket. But also, there are different weights for them.
Okay.
And because the classifier itself, it's more or less a tree, so actually these different locations get automatically sent to different branches of the tree.
So there are two kernels here. One of them is the kernel on the patch, the other is the kernel on the context on the weights for my neighboring.
Yeah, but in the end, for the classifier, it does not distinguish them. So it just because when you feed the classifier with all these features, so the appearance feature and all these content features, you just line them up. So you don't separate them in the training. Yeah.
So how come these two red squares at the top of the last? I mean, I would have thought that if it's only support for the horn, there will be on the very bright areas that you get new features in the context.
But you also have the background support because every picture shares the same classifier. So sometimes you want to suppress the background. Sometimes you want to enhance all these things. So it's not necessarily just all from the object body.
Negative weights.
Yes, you get kind of negative weights. Yes.
Red could mean a negative weight or a positive weight.
Yes. Yeah. So because it's not only on the foreground, also on the background.
If there's no spatial information involved, I could have understood that if the belly features in the center, then it would expect background to be high up in the sky.
Yes.
No more horse, but how come it knows that now if you're saying it doesn't use the spatial information?
So the spatial information is from all these pixels. So each pixel here, each dot over here is one particular feature. So the spatial information is implicitly carried. It's not like, I want to check 3 meters away, there's something. It's here, so I check based on my point. If that feature is selected, then I'm going to check the probability of that guy. So the spatial information is still there. It's really important, but it's not just explicitly carried as saying, you measure the probability for along the stray and put something like that. So it's not explicit.
Are you worried about that he's using the same classifier for every pixel? And therefore, like, you would want a different classifier for like the feet of the horse, say, than the upper back, right? But you use the same classifier.
You use the same classifier.
And it works.
It works. No, in the talk, I was trying to separate the type of classifier I'm using from the problem itself, from the modeling problem itself. So what I did, realistically, was I had the so-called probable boosting tree I developed, but you can use your favorite one. So it's like the classifier itself, or trying to classify the multimodal kind of classifier thing. It's not like a SVM, you have weighted sum of everything altogether. It's pretty much a decision tree. So when you decide all these, it's automatically embedded in the classifier. All these, yes, exactly. So all these different locations are actually in different branches of the tree. So it's automatically done by the algorithm.
Okay.
Yeah.
I think you use your favorite for these two
Yeah, but you can use other, yes, yeah.
So the only invariance that's built into this a priori is just translation invariance. Any other invariance you have to get from your training?
Yes, yes, yes. That's right. Yes, yeah. And also, you can put the position as a feature as well. The position of each pixel as a feature as well. That helps in some particular domain where you know the structures roughly. Yeah.
But you didn't do that here, right?
For this one, I didn't. So this is the result on the test images. So these are from the so-called Weizmann horse data set. And so these the first are the input images, step 1, and these are the final results. As we can see, the results are much better. And also, these are almost the worst results on this data set, on the test image. Even on these, we can see this is a really dotted kind of texture horse, but still results are not that bad. We pretty much get the best results on this. And it's really fast. Usually it takes about, I think for this one takes about 15 seconds or 10 seconds.
How many inputs in this training set?
It's 128 images.
And if you showed a picture without a horse, would it hallucinate a horse or would it have it be all black?
That's a good question. I'm going to show you.
Okay.
Yeah. So these are some comparisons in terms of the asymptotic behavior of the algorithm. So first is to compare. So first iteration, you start from image appearance only. Then these contexts start to kick in. You can see the higher the better. It's F value. So this is tested by the auto contact. This is training error. So we're not doing too much overfitting. The algorithm pretty much is symptomatically kind of keeping the same thing. And one question about context is people ask, what if I just add all the appearances?
Remind me what F value is. What's tested?
F value just, let's say you can consider it's average between precision and recall, detection rate. Yeah, so the higher the better. Then one thing people would say, instead of computing all the probabilities, just enhance or enlarge my appearance feature pool. Instead of looking at all the probabilities based on previous, I just look at the appearance on all these locations. So consider the appearance as a context, directly put them into classifier. But it was not that good. So once you do that, you pretty much end up with overfitting. Because it's very easy. So now, if we have 1 million features, it's very easy to perform the classifier, but it's hard to be generalized to the test image. So that says actually these are the things I did to use as an appearance feature, and the results are significantly worse than using this kind of context type of procedure. So these are the results on the Horseman data. And the curve actually does not tell too much good. So this is our recent result. These are the results by the Berkeley people. It was way above. But actually, this is also due to the measure. This F value in terms of foreground and background. The results actually get much enhanced, but in this particular data set, seems like it was not showing.
Well, yes, no, it's a horse per image or per
pixel.
Spatial pixels.
That's right, because you even put the black box over there, you still get like a 70 or 80% of the accuracy there of F value. So that's why in this particular one, it's not that illustrative. And also, I did several interesting experiments to test it. First is, now remember, we have the appearance, you have the probability map, you put them together. So one question is, in the second layer, what if I just learn, you use features from the probability without the appearance? So now, before I have the appearance, the second classifier still use the appearance. But interestingly, 90% of features selected by the classifier are mostly from the probability map. The appearance ones become less important. But now let's completely remove it. So these are the different results. So this is the regular auto context. This is so this is the one without the appearance. So starting from the second layer, no longer the appearance feature is no longer there. So it still works. Yes, yeah. Yes. So you can see having the appearance layers is still a good thing. That says one message I want to sell here is, in the previous study or papers, people pretty much separate appearance from the prior, all these things. But here, we really want to integrate them together almost seamlessly because it's really hard to tell when is a good time to throw away the appearance. The whole modeling part, we should keep them together if we can. So another test is after the first classifier is trained, after the second classifier trained, instead of train another one, I just repeat the previously trained the second one. So these are the results. So if you would just repeat, you see, the algorithm is still good, but this one probably drops down. So this means at least at this level, you can push it up, but in the end, it drops down. So this means that probably it's not generalizing very well. But you can, if you do this, actually still can improve the results. So if you cannot afford too much training time, you can just repeat from the start. It's like now, before, we have a dynamic graphical model for the algorithm to choose. But here, we fix this model. Once it's trained up by the second layer of classifier, just fix it. So it's the algorithms, the performance can push it up, but it's not ideal. So that goes back to your question. So all the images are from this particular data set. I just go to Google, typing horse images, I get these things. So these are the results. And particularly interesting is this example. You can see all the horses are facing to this direction. So you can call this either a failure or success. Failure meaning this small horse is not segmented out. Success, you can see almost carved out. The algorithm almost carved out this small horse. And also in the training, there are only one horse in all these two images, and then all here we have multiple. And these are the trees, which are pretty much black. You can see they're not segmented out. If you would run a traditional segmentation algorithm, you will have all these junk type of thing over here. But this is just illustration to test how the algorithm is able to generalize, and it's not really overfitting a particular data set. Yes, yeah.
I mean, did you try like these flips of hyper horses? Maybe you can handle this one.
Yes, yeah. But that's just I wanted to show. It's an interesting thing to show. It's able to carve out because that's why I'm saying it's either success or failure. But if I would really build a coarse detector, probably should. Yeah.
I mean, you could also look at this as what you're learning is a not grass detector.
Yeah.
Just to be.
Yes, yeah.
So it's kind of hard to tell. Do you have some images which aren't grass, or it's like, which are a little more different to see, kind of get an intuition for, is it learning what a horse is, or is it learning what grass is not?
Yes, that's a good. Probably these mountains are not grass, but that's a good point. Yeah. Yes, pretty much still yes. Yeah. I agree. Yeah.
For experimenting, did you try some random where there's no horses inside that, and just some random background to see what the output is from there?
Maybe you put a person.
Yeah, I put a person. Yeah.
Put anything else on the grass.
Yeah, but all these are very good, suggestions to test. So the convergence, I probably will skip the details. The convergence is guaranteed in terms of training because every time we are guaranteed to monitor. So, and also then now goes back to David's question. So now instead of a single object, now what if we have parts? So I collect all the data. At that point, I was not getting too much help from graduates, so I did everything by myself. So annotate all the parts, head, body, torso, feet, all these legs. So there are 14 body parts over here. So these are, so I collect 120 images from Google, and this is the separate data set from Berkeley as a test images. So these are the results by the first layer, only based on appearance. As you can see, the body is pretty much there, but still very fuzzy. Head, we almost completely lose the head. And the feet or thigh, all these things. So the second layer start to pick up it because once you have kind of rough information about the body, then using the body information, head cars come out. So here, again, as I said, the algorithm is very general. So it does not distinguish between two-class problem or multi-class problem. And you just stack all the classification map, and it's up to the learner to decide. So now, between objects, contexts become important, and they're being picked up. So this is the fourth layer of classification. We can see head is pretty robust, body is there, feet actually has almost all picked up, but some of the thigh missed it. So this is more implicit kind of thing. So next level I'm pushing is more explicit to carry information as a context, hope to better. But this pretty much gives you a picture of how this thing can be done. It's really fast compared to the traditional kind of body kind of segmentation. It just takes seconds to perform.
So here actually you build this one classifier per part.
That's a good question. So again, I'm putting this whole multi-class classifier as a black box. You can choose your favorite one. But I actually, recently we did this so-called data assist output code. You don't have to have so many of classifier. You just have a coding strategy. I'm going to talk about it shortly. And then you only have to need to have log to the k a number of classifiers instead of if you let's imagine if we have 1,000 classes, cannot afford to train 1,000 classifiers. So this is a more recent kind of 24 class MSR C data set. They annotate 24 classes objects and in all different background. So these are the results by the algorithm. So sky and person, all these things. So both is okay, but some is confused with road, water. So this is a little bit confused. Sky. So some, but street scene actually is pretty good. Road, car, sky. These are the really good classes of things and things like that. So this is the confusion matrix. At that point, we pretty much got the best score on this data set. And Sharton's algorithm at that point was 72.2. And another thing is our confusion matrix is much better than the existing one at that point because we're making reasonable mistakes. So if something was confused with cow, it's confusion between cow or sheep, not like a cow versus car, things like that. So these are some new extensions we did recently. So so this is so-called a new multi-class classifier data assisted output code. So it speed up the training and testing process drastically. Then we also have the scope space approach, and then also region-based voting scheme. But for that one, for the last this year's CVPR report takes about 30 to 70 seconds for this multi-class labeling. So then the region-based speed up drastically. So yeah, this is a new multi-class classifier. So now suppose you have 100 or classes of labels. If you would do a one versus all, you have to learn 100 classifiers. So here we did a so-called output code type of thing. So each class, there are different bits. Each bit represents a classifier. So for each bit, it randomly give it a, yeah. So the existing work pretty much gives a random coding bit to different classes. So if you don't have any redundancy, you don't have any error correction capability, you only have log 2 to the k number of bits or classifiers. But all the existing work does not look at the data. So now suppose you have a 4-class problem, the existing work pretty much does a random kind of coding strategy. So if you would do random, you will combine these two classes into one, and this is your, let's say, your foreground and background. Then your classifier will have much more difficult time than looking at the data. So this new thing looks at the data by assigning this, when you assign the bits, you look at the data first. And then ultimately your classifiers are much more reasonable. And also, it balances between the training and the computing time. If you were to do one versus all, you have to have so many of the classifiers. But here you only have log. So overall, it's much better than the one versus all the existing ones by looking at the data.
When you say look at the data, are you looking only at the first layer, at the results from the first layer?
Oh, okay.
And using that one to...
No. So I should clarify. This one, it's a standalone machine learning algorithm. It has nothing to do with the outer context. You just consider this as a multi-class classifier. I give you the features. You just obtain a classifier.
So you are just using the first layer.
Yes.
You're using just the features, just the patches.
Yes. But
because one could imagine doing the same thing but with higher.
Yes.
And have you tried adding more than log n bits, but still many less than?
Yes.
Because I'd imagine it would get much better if you would. More.
Yes. That's what this figure is talking about. So you can see this. The x-axis is the number of bits. So up to this point, they already can classify them. So if we add more, the first couple of bits will drastically improve the result. But afterwards, it elaborates kind of things. It depends. Also, we almost tried 10 UC Irvine machine learning data sets. So we want to get this thing clear without looking at the image data, because that's the good thing about machine learning. We work on some toy data, but then we get the understanding of how the behavior is. It varies on different data sets. Sometimes for one particular data set, it's better. And if you push more, it's going to be better. Sometimes pretty much leverage. But in general, adding error correction capabilities always helps. Yeah. But you need to balance.
Sometimes that's not really convergent. It does not, even though you add more bits, it's not going to get a performance.
No. After a certain stage, I think it's not going to improving too much. Yeah.
It's probably talking something about the intrinsic difficulty of the first level.
Yes. But again, this is a separate thing. You can consider just a traditional, just a machine learning classification almost has nothing to do with the image, but just.
The replacement of the original black box you used in your algorithm.
Yes, that's right. And we speed up the training and testing process largely. So then talking about the scale. So now, because there are very limited number of training images in there for each class. And if we do it only a patch-based, a fixed patch size, patch-based kind of approach, we throw them together, and if we, let's say, consider it as a two-class problem, it's dog or sheep. You can see for some dominant, if the scale is really right, then these kind of structures are far away. If the scale is not right, and these patterns are confusing, this means this is something about so-called margin for the classifier. So if you are at the right scale, then the margin is big. If you're at the wrong scale, then margin is small. So then we want to design this algorithm to automatically look for the scale. So there are two options. One is doing the so-called multiple instance learning. Each pixel, you have multiple instances, and you consider the back, the only right one is the correct one. So it's a weakly supervised. The algorithm need to look for the specific class scale. So there's another thing here. We did a very simple thing. You just for each pixel, you collect different scales and throw it into a classifier. The classifier automatically trains. Then in the testing, you also compute different scale. So for those dominant scale, it will tell. For those fuzzy scale along this decision boundary, the decision is weak anyway. So then in doing this way, we handle the scale invariance problem better than before. So does this answer your question?
Well, what do you get actually? You actually, at the end, you get the size, the correct size?
Yeah, so you don't get a specific, but once you train your classifier, then you have your classifier. You test on different scales. The good scale is far from the margin. This means it's high confidence. The bad scale are fuzzy, so it's along, let's say, probability. Yeah.
But then how do you, when you say classify, you mean, I thought you were trying to determine what scale is right.
Yes.
So at the end, the classifier gives you a number.
A number, a confidence.
Scale. But I thought the scale is different for different images, right?
Yes. So that's why for each image, for each site, you try for each pixel.
Each image, you find the scale.
Yes.
Not just the image, but for each site.
For each pixel.
For each pixel.
Yes, yeah, not for just.
You choose maximum response across skills.
Yes, yeah. So there are a couple of options we try. First, you can compute what is the dominant or the skill which gives you the lowest entropy. The lowest entropy, or you can just vote them together, put them together, and let them carry the uncertainty.
The magic choice is to run to train your classifier using the multi-instance scheme to automatically figure out which examples.
Yes.
The correct one.
Yes.
The training test.
Yes, yeah. So these are all the options, and
Are different scales informing each other if you do this? It seems to me like you're picking, in this case, an optimum scale, but you're not necessarily using multi-scale in the richest possible way.
No.
Where a small feature and a large feature can work together to. Am I mistaken? Or?
No, we do not explicitly do this, but all these small scale implicitly carried over there, because in the end, the best strategy actually is voting.
Okay, so you do end up using a mixture of scales at the next level up.
That's right.
Okay.
Because we tried to obtain the smallest, the patches with the smallest scale with the smallest entropy. It helps, but not that significantly. So what we did is we just compute all the different responses from the scale. I just average them together. So it does have different scales now. And because sometimes if you have dominant, this one will dominate. But you also get some help from other scales. So
you're taking the average response of all the different scales.
Yes.
So then, okay, so I was going to ask you if each patch independently chose its scale, but if you take an average, it doesn't really matter, I guess. So.
that's right.
All right,
Is average better than max? Right?
Yes, in many ways. That's why recently ensemble learning takes off than many of the alternatives. Ensemble learning really helps. Yeah. So then we do another thing called the region-based voting. Given image, so in the previous one, we just scan each pixel and compute all these things. It's fast than the existing one. Still, 1 minute is something I'm not happy with. So what we did was we do a simple kind of k-mean or mean shift type of class color-based segmentation. It's 0.1 second. Then you obtain some region. So now you don't have to scan all the pixels. You just scan subsample, let's say 5% of the pixels. Again, going through the scope space, obtain the proper map. And now it's much faster, and also the boundaries are much more accurate. You can see this is the result by the previous auto context. You can get the whole body, but you can see it gets dilated. But here, the segmentation, the boundaries are much more precise. So this is a recent work.
Colors segmented really well, so it's.
But that's one thing. For many of the color or the real images, using color information, if you do a little bit over segmentation, the segmentation boundary is very precise. You just have over segmentation. So the problem is how to do a grouping to combine them. So we do have a really help. So you can see the cow segmentation. It's significantly better than before.
This is more like this kind of more straightforward silver pixel.
Yes. Yes, yeah. To speed up, so this is submission to CVPR. So in terms of significance, we have 3 pieces: scale, space, multi-data assist, multi-class, and also this one. In terms of significance, it's less than the original auto context work, but it improves the result, improve speed. So then later on, this algorithm is directly illustrated on the brain image segmentation. Now we have a 3D volume. Each voxel has intensity value over there, and the task is to perform brain segmentation. What we want, and pretty much our lab's dream is to build up a brain Google or have brain image analysis engine like doing a blood test. When you do blood, you take a drop of blood, you do the analysis. Here, if you just go through the MRI scanner and obtain a 3D MRI image. You have different structures segmented, and then you can study their shape, their different relationships, cortical thickness, all these things. Then you will know what is your age based on the brain, what is your mortality, all the disease, or whether it's HIV, in fact, Parkinson's disease in their early development, all these things. So then for brain 3D segmentation, manual indentation, obtaining manual indentation is even harder because we can only look at one particular slice. So it's hard for the humans to obtain consistency, even for human. Because you see, if they manually segment the structure from this corner view and from the sagittal view, it's bad because you just make them smooth over here, but from the other angle, they're not. So even for humans, it's a very hard task. But the good news for this particular domain is the structures are more or less there. If you don't have hippocampus, you're dead or alien. So the problem is much better. So we almost use the identical procedure. And the only difference now, instead of putting 2D features, you have 3D features. That's it. So this is the task for segmenting the caudate. And this is this grand challenge computation. They have brains from different machines, Siemens, GE. Then they have ground truths. Then they also to train and segment. And recently we did the test on segmenting hippocampus. Actually, this curve shows our results are actually more consistent than human subjects in terms of results ground truth label. So in 3D, we are even outperforming human subjects because of this constrained domain. In 2D, we're hopeless. It's still far from being able to outperform humans. But in 3D, in this particular constrained domain, we're able to outperform human subjects.
So how do you determine that you outperform?
That's a good question. We perform like a consistent measure, p-value, in terms of predicting the disease. Yeah, it's the ultimate outcome. So it's no longer based on ground truth segmentation. It's based on predicting the disease. And also, we recently did a study on the monkeys, what they call the vertebrate study. It's a genetic study. So they have a whole zoo of monkeys somewhere in Los Angeles. I don't know where they get that. And it's not the Los Angeles Zoo, but they have like a mountain there. They captured, I think, around 300 monkeys, or maybe no more than that, 800 monkeys. They hire a truck, and they rent a truck. They hire a person, then they put the MR scanner in the truck, and they just scan the monkey brains. So then they study this inheritance or genetics, all these things, and our results are really more significant, but much better than results by humans, because graduates or even some neuroanatomists, we cannot guarantee consistency. We get tired often the times. So then we do a full brain image segmentation for 58 structures, and now we have this so-called pipeline is up in the web. Everybody is welcome to download, and it's being widely used in the neuroimage domain. So it's a real product. It's not like a company product. We're still research-oriented, but it's being widely used by many neuro scientists because they have a scan. They just want to segment the structures. So this is just a little illustration for the brief propagation in terms of MRF and CRF. Again, as I said, brief propagation needs to propagate the message very slowly to the point of interest, and the models are very limited because we were forced to perform integration, and that's why the modeling capability of the existing MRF and CRF is very limited, because we can only afford to use or have very few number of connections. But here, we can have a very large number of connections. So then computing is what I emphasized. What you can learn is what you can compute. The testing almost shares identical procedures as the computing. So the only difference is this generalization error, but that's it. So you don't have to have a very heavy algorithm design. And for the identical algorithm, it works on this horse, all these different things. So the conclusion for the auto-concept part is we learn low-level context model in integrated framework. So that's important because we don't want to distinguish too much from all these high-level from the low-level. Although this is still black box type of thing. So the new thing is to push for more explicit. Very easy to implement, significantly faster than the sampling or image minimization algorithm general, and avoid heavy algorithm design all these things. But also it has disadvantage. It requires training for different problems. So for some distributing work, you can define your energy, then you can use off-the-shelf algorithm. So that's a disadvantage. But the disadvantage here, you need to train. But for solving really the difficult problem, probably it's hard to define some energy and apply off-the-shelf algorithm. That's at least one doubt I have. We have to look into the structure of the problem. Training is long, but now we reduce it significantly. Require labor data, but it's not. Actually, we're pursuing weekly supervised, unsupervised in this domain. Since I have a little bit of time, probably I'll just spend 2 minutes to think. This is something I really like, this year's work. I really like. So we talk about this segmentation. Shape understanding has been a long-standing problem, and this problem bothers me a lot. As even we have the shape of here, how do you tell this is a horse, this is a dog, and this is a cat, and this is a dog, and this is a mouse? So sometimes local parts can tell you a lot. This is typical horse kind of gesture, and this is typical dog. We're less frequent to see a horse like this. And also this kind of shape is important. So local parts tells us a lot of information. But sometimes the global information is also important. Because you see, this is a cat, this is a dog. Local parts, they're very much similar. But this bumpy type of thing pretty much says it's unlikely to be, although cat sometimes do this kind of thing. So local versus global. And also, if we have highly articulated objects or non-rigid objects, the deformation is important to kill, and it's hard to be captured by local parts. So you see, these are the two mouse. They are viewed from completely different views, but so the parts are different on the contours, but the skeleton information is more or less similar. So if you compute the skeleton on medial axis and compute the radius sequence on these big, these discs on the, they're more or less the same. So there are now three concepts. One is contour versus skeleton. Another is local versus global. So how do we really understand this is particular shape information? Put them together. I'm not going to go to the math, but conceptually it's very easy to understand. This is recent data sets we collect for 20 objects, and it's almost the most difficult shape data set ever. And this is a dog class. You can see the large variation: deer, crocodile, bird, butterfly. So even I give you a well-segmented objects. How do you tell? You see, this is way beyond the understanding of elephant, and the monkey or the cat. You see the large variation. Then how do we really do this? This problem puzzled me a lot. So one thing we did is very simple. So given a shape, let's say consider as a contour, we perform a simplification as a polygon. And you can extract these high curvature points and you put them back. So now you have points. So for every pair of points, you can have a sequence. You throw them into a same space and normalize them, you obtain signature. So this is one PAMI paper my student had. So the source code is there. Everything you can repeat. So it's very simple now. So given a shape, you compute the high curvature points, so these key points. You throw all the pairwise type of features, these kind of local parts together and normalize them. That's it. So that's about your contour. And also you can compute the skeleton. And you also obtain these kind of high, so-called endpoints. And you for every pair of endpoints, you have a path from one point to the other. Then you put the disk, compute the radius sequence. So this is very robust against junction because if you have multiple junctions, that's typical in skeletons. You only compute the path. So it's very robust against the junction. And you obtain another set of features. So now you have two sets of features. You just throw them away, so throw them over there, and consider put the nearest neighborhood classifier on top of it. So that's it. There is some kind of play with these two type of features. I'm not going into the details. But so now you have two sets of features. One is from the skeleton, another is from the parts. But here the scale information is automatic carry because you just put every pair. So you cross all different scales. Every pair of points are there. So, and you obtain a nearest neighborhood. So this is a result on our data. So on the famous MPAC7 data, in which there are 70 structures, 70 objects, each has 20, we get 96% extra classification rate. So that's evident that particular data set is not difficult. So on our data set, so we compare some of the existing work. We obtain 78.7. And many are the existing matching type of work. It's slow and the results are much worse. Let's say shape context or these matching-based algorithms. And this is a matrix for different objects. CS meaning only use contour segments. SP is only a skeleton path. And CS and SP is the combination of them. So you can see it's very interesting. The combination of them always gives a better result. And so for this mouse category, you can see skeleton path tells a lot. Because on the contour, it's not that robust. But the skeleton, because mouse is highly non-rigid or articulate, and it's non-rigid. So skeleton path is very informative. For some objects, let's say bird, this contour is very informative. The mouth of this bird, their particular, and also we don't have to explicitly worry about the scale, and there's no explicit matching. So we really get very good results. And this is on the real data image. So we have the horse and the cow. You just learn a classifier to obtain. So this is the problem map. You do a binarization. Then you obtain these are the masks. So then you train your algorithm. We obtain 96.5 accuracy recognition rate or classification rate on the horse and the cow. So I'm quite happy given this thing because, as I said, the problem puzzles me a lot. But by a very simple play, we were able to combine the contour together with skeleton, and you don't have to explicitly worry about the scale, and avoids the explicit matching kind of thing. And even we're given well-segmented structures, it's hard. But I think given this kind of work, we push the general shape classification to the stage where things can really can be naturally coming out.
Sorry, I'm not understanding what you're doing with the real images now, because that's how do the contour segments and skeleton paths relate to these real images?
So real images now, in the training, we have the label map. Then you just train a classifier in terms of segmentation. Now it's a foreground and background segmentation. Then you obtain a problem map in terms of the object, but you don't know which one it is. So you only think.
You're using the training data from that set.
Yeah.
To
obtain segmentation.
And you're doing just the outlines of those.
Yes.
In your technique here.
Yeah.
And then you train up your image based using the so. Yeah. So what's the middle?
So the middle, this one is the classification problem map. So once you obtain the problem map, you just do a simple binarization to obtain the segmentation. So here it's a fuzzy map. Then you just make a hard decision to obtain segmentation.
So your contours
coming from here.
The binary map.
Yes, from the binary. Yes.
But
That's your performance.
Yeah, that's the performance.
you train on this kind of images.
Yes. Yeah.
This kind of contour, not the.
The training is on the real contour.
Real contour.
It is a manually annotated contour. So this says, even you have really bad segmentation results, the algorithm is still robust because you see the parts are missing, but because of all the other parts are, yes, that's right, yeah. Yes.
For this specific image, I see probably the skeleton will not give you much.
But you see, there's still skeleton, you see, 85.
See, but for some
For some, yes, yeah, for some. It's again the overall. The message is combining skeleton with the contour really helps. And here, we throw everything into the space as a nearest neighborhood. It's kind of very simple, but it captures a lot of the essence of the shape problem.
Really, the message of this is just that it's kind of a testament to the robustness of the original algorithm to having pieces of missing.
Yes, yeah, occlusion, all these things. Yes.
Right?
Yes, yeah.
I mean, in a way, this is a very roundabout.
Yeah.
Seems like a very roundabout way of doing, what might have been a simpler. Yeah, I mean, I would have liked to see just with occlusions or with noise of other kinds like this. How does it degrade? And I'd imagine it would do very well.
Yes, yeah, because on all these images, you already have large occlusion, self occlusion. Yeah, self. But the question is, how do we? Because nowadays, if this would be 5 years ago, we don't have to show the results on the real image. But now people always ask, how does whole thing work on the real image? So that's why we want to show that it can handle errors in segmentation, and because many times the parts already tell you a lot of story. But if you would do a matching, it's really almost impossible task to match all these parts all together, because you have to handle all this scale problem, all these things. So it's kind of implicitly getting away from explicitly matching the parts, and how do you combine the contour, all these things. So I think the message is clear. Yeah.
The results here, are they horse versus cow?
Yeah.
Okay. In the cow data set, if I remember correctly, they look very similar to the cows that you show here. So the cow data set's very similar. It's all cows in the same background, moving along in the same direction. So do you get a sense for the classifiers kind of recognizing the cow's head, and then that's kind of like the main?
Yes,
that's one benefit of your classification. You can say, I recognize a subregion, which is a cow's head, and that's actually acting as my main yes/no gate.
Yes. So we have to look into the details. Which one? Yes. It was just recent CVPR summation. Yeah, okay. But that's a very good question, because sometimes just this particular chunk already helps.
Potentially that has very good repeatability.
Yes, yeah. That's.
At first stage, you can segment that part out also very robust.
Yes. So I think in a sense it's artful play with a very simple technique, and without going too much hassle with all these. So you can see even this chunk is completely wrong, but all the other parts can play the role. Yeah.
So if you could move back, use this condition information back to help with segmentation.
Yeah, that's a good question. So that was actually part of my proposal in the ONR, which is funded. So to combine them together in a loop. Yeah, into shape prior. Yes. Yeah.
It's part of the definition.
Yes. Yeah. Okay. I think that pretty much concludes my talk. Yeah. Thank you so much.
Things that I have two. Sorry, just 2 more questions. Sure, we've asked 2 more questions.
We still have 15 minutes.
Okay. So one just has to do with kind of relationships between what you're doing and what happens in visual cortex. I mean, one of the things that's kind of cool about this is that your immediate propagation of information between distant, or in your case of scale invariant, very different scales in one step, seems to me a little bit like the kind of connections that happen, say, between V1 and V4 directly, or these connections that go directly through intermediate layers.
Yes.
And it's the first time that I've seen a kind of cascaded model that has those long-range connections across layers like that. But the other thing that's also happening in visual cortex that hasn't generally been modeled very well in these kinds of things is feedback.
Yes.
And so I'm wondering if you've thought about incorporating feedback more.
Yes.
In the sense of taking your later results and then improving earlier layers not using the more converged knowledge that you've gotten there and iterating that way.
Yes, that's an outstanding question. So my previous research, Gan actually knows quite well, is the so-called data-driven Markov chain Monte Carlo, is to activate the high-level part, but driven by the low-level part is the feedback. But recently, I'm a little bit moving away, at least at this moment, from there, because if you do this, the learning and computing part is pretty heavy. But here, you can see every step is feed-forward or deterministic. So you can see you can push the result to a certain degree, but it's far from being perfect.
It also makes your learning non-convex. Right?
Yes,
so it gives you all those problems.
Exactly. So in the end, we still need to bring the other knowledge. So another direction I'm pursuing is to combine the so-called implicit and explicit information. So I'm not happy with the current stage where many things are implicit. I want to be more explicit. So then there's so-called unsupervised, supervised, and discriminant generative model. All these things, I want to put them together. So that's a more recent work I'm doing to put more into a group rather than feed-forward. It's like traditionally I did this whole heavy computing of top-down, bottom-up. Now I'm trying to get away from a little bit. Yes, one way, because many of the information, just like we can decide very quickly. Then once these things are more certain, probably we need to bring them back. Although this feed-forward way is there is information being propagated, because when you do the classification, some other parts already tell if this part is dominant, already gives you the information. So there's indeed some kind of the feedback over there, but it's not like what you're describing. So
there's plenty of reaction type data for psychophysical results on these things that suggests that the feedback is really important for learning,
yes,
but is usually not important for discrimination, for the actual detection.
Yeah.
Because otherwise you can prove that it would take too long.
Yes, yes. Right.
Okay, well, my other question is whether you've thought about applying any of these ideas to text.
That's great. Yes, yeah, that's something, yes, I want to do. So here it's an image. I really want to apply it on just language or text understanding. Yes, one dimension. Yes, yes. I actually tried on one particular case. It shows improvement, but I haven't got a chance to really work hard on this language because I think it's natural compared to the existing CRF model, existing language model. I think
that's a very special interest to me, and I would love to to maybe communicate a little bit more about
Sure. Yeah. Yes.
In your brain segmentation, how many structures were you segmenting?
56.
And were you using an atlas to drive the segmentation, or?
So it's similar to this one. We have 40 brains manually annotated. You can consider that's an atlas. Then you train your algorithm. Yeah.
Each of them had 56 structures in it.
Yes.
Okay. And what was the range variation in shapes?
I think it like a 20 are control. 20 like there's 10 Alzheimer's disease, 10 like a schizophrenia disease. So yeah. So, but I don't know have a detailed description kind of because it's very hard to compute the variance for the structure because it's 3D.
So I see. Okay. And these are do you know the MRI machine specifications?
Mostly Siemens, I think.
Or
okay. I can look into the paper. I recently sent out paper, but.
So what kind of visual features for those MRIs? Those are brain images. What kind of visual features?
So here I pretty much use gradients and also some of the 3D HARs and the curvatures, mean curvature, Gaussian curvature, all these.
So intensity is not very.
Intensity. You should use, but intensity sometimes is not robust. For one scan, you can have intensity 100. Another one you can have 20,000.
Well, so varies a lot.
Yeah, varies a lot. One thing you can do is to normalize the intensity, but it's hard to normalize them completely. So gradient informations. Yeah.
That was great.
One more question. What was the smallest structure that you segmented in the brain?
I think hippocampus.
And what was the accuracy? Do you remember?
I think hippocampus is the worst. I think around 75. Yeah, hippocampus is worse, especially the tail part. Yeah, it's been the most difficult structure. Yeah. Okay, thank you.